So what I'd like to do is introduce an alternate way of doing things, which is the LifeTrack device, which is basically a new type of electronic device that's part VVM and part electronic temperature logger. And I have to say, you really have to understand this as being a cross between a VVM and a temperature logger. People tend to either see it as a VVM and go, well, that's too big to put on a vaccine vial, or they tend to see it as a temperature logger and go, well, we got those. And the answer is, what you don't have is a VVM that works or a temperature logger that lets you see at a glance if vaccines still work. And that's what a LifeTrack device does. Now, LifeTrack was inspired by the vaccine cold chain VVM tags. I mean, the idea of being able to glance at something and see if it's still good or not is a great idea. We just want to make it work. Here we can take advantage of the fact that although it's really a horrible bear to come up with a chemical approach to do the complex vaccine stability, electronics can do it. And for microprocessors these days, they're getting so small and cheap, microprocessors cost like 25 cents now, that it's possible to do the equivalent of throwing a personal computer of the 1980s at a vial of vaccine and have it compute, is the stuff still good or not? And that's the basic approach, is to come up with a little electronic tag that can be programmed with the vaccine's characteristics and stay with the vaccine for years if necessary and keep track of what's happened to it and let you know at a glance if it's still good, and if it's not good, tell you what happened. So the questions are, of course, how do we do this, and can this really be made reliable and cost-effective? Well, in terms of how we do it, here's an actual working prototype on the upper right, and I want to stress prototype. It's a proof of concept, not the final high-volume production device. How we do it is we basically program a very low-power microprocessor in this tag with a little computer program that basically runs this little loop that called the stability bank algorithm. And how this works is really a lot like one of your automatic teller machines, an ATM machine, where at time zero we put a whole bunch of stability points in the stability bank. And we also tell the little microprocessor, well, every minute or every hour or whatever, withdraw points from the stability bank. And we say, well, depending upon how many points you withdraw from the stability bank, it's going to be a function of temperature. If the vaccine is in a temperature regime that it likes, then only withdraw a small number of points per minute or hour. But if a vaccine is being stored under conditions where it's dying rapidly, then withdraw a high number of points per hour. And you can see how this can, if we get that rate of withdrawing points right, then we can mimic a vaccine's characteristics. And on the right is a graph showing of what the algorithm looks like for insulin. Now, going into a little more detail of examples for real vaccines, here's an example comparing oral polio vaccine, OPV, with hepatitis B vaccine. OPV is the thin line on the graph on the left, and hepatitis B vaccine is the thick line. And what we see on the graph is on the y-axis, graph on the left is the y-axis in days, how long any days can last before it goes bad. And the x-axis is the storage temperature. And we see 0 is displaced so that the graph goes from minus 20 degrees to 0 degrees to 20 and then 40 degrees centigrade. Now we see for the thin line, oral polio vaccine, that the colder it is, the better. This vaccine loves the cold, and if it's frozen, it says, that's great, I love it, I'll have a really long life. And as the temperature gets warmer and warmer, of course, it doesn't like it and it dies quickly. By contrast, hepatitis B is a much more complicated curve. And here the problem is that, as we mentioned earlier, this vaccine dies if it's frozen. So its stability lifetime falls off a cliff at around 0 degrees centigrade and is dead. If you freeze it, it's dead. However, if you don't freeze it, it has very, very long lifetime, and here I've truncated the top of the high lifetime to fit this thing on the graph. But again, if you get too hot, again, eventually it will start to deteriorate on you. Well, the function of temperature that you can program into the LifeTrack unit to make the LifeTrack unit act like the vaccine is shown on the graph on the right, and you can go to the paper and vaccine paper I wrote in 2006 and analyze it in more detail offline. Suffice to say that this tag can be basically brainwashed into thinking it's one of those vaccines and acting like it, and more importantly displaying its status. So let's zoom in on what this prototype looks like. We see the prototype circuit board on the left, and there's a little programming port on the bottom where the data, the function of temperature, is programmed into the unit. It has a little battery, and people say, well, geez, that's a coin cell. We can't put that on our boxes of vaccines. And the answer is, again, this is a prototype. Much more elegant devices can be made if there's real interest in this concept. Has a display, liquid crystal display, and these prototypes can run for about 3 to 5 years. They actually, in theory, should run for about 5 years because the microprocessor used is very low power, and so these can last for a really, really long time. And how their work is basically you make a large number of these generic tags, and for each tag that you want to be a particular vaccine, you hook it up to a programmer unit, and you basically download the stability characteristics for that vaccine into the tag's memory, and then tell it to go, and it will start thinking it's acting like the vaccine. And now what happens as this thing is stored is that the tag, the little liquid crystal display in the tag, will gradually change. When the vaccine's fresh, you'll see a big plus, and that's just meant to indicate to people they can just glance at it and go, hey, a plus, it's still good, that's great. And little 4 bars just show what percentage of the lifetime is left. And 4 bars basically means like, hey, we've got a full vaccine lifetime ahead of us. If the vaccine has become somewhat aged, but still good, let's say it only has half of its lifetime left remaining, then the 4 bars may go down to 3 bars or 2 bars. And the 2 bars eventually become 1 bar and then no bars. And finally, when the vaccine really shouldn't be used anymore, the plus will turn to a minus. And again, someone can just glance at this and see, hey, this stuff shouldn't be used anymore. And if necessary, start doing a little investigation if that minus is showing up too soon. Now, what I would recommend is putting of course, a more refined version of the LifeTrack unit on vaccines at sort of the box level. That is, for example, 1 per every 10 vaccines. And this diagram, you see this LifeTrack unit, an updated version of it, and the little blue line basically is showing that you may want to have a configuration where the temperature sensor is actually sticking into the center of the box to get a more accurate representation of what the vaccine temperature is there. So here you can have the display on the outside of the box, but you're monitoring temperatures inside with a little thermocouple mounted on a wire.